Okay, so can you hear me? Good. Okay, so welcome to this second lecture on discrete mathematics. And today I'm going to start with something very basic. Whenever you want to play football, where do you go? Football field. Whenever you want to play cricket, you go to cricket field. So whenever we want to play with mathematics, where we should go? Huh? So we go to field. There is a concept of field. Field means a set where we can do all the four operations: addition, subtraction, multiplication, division. That is a field. That's why we are able to play, right? If we are able to play with all the operations, so that set is known as field. So in fact, before field, I just briefly, this is, I think, probably you might have heard about set of natural numbers. इसी class में पढ़ा होगा, right? Maybe class 3rd, 4th, I don't know, 5th. Set of natural numbers, right? From where they came? Did you ask this question? Who invented natural numbers? Name says that, right? Prakritik sankhya, which appears in nature, right? So when you start observing nature, you observe these things. Actually, natural numbers started from counting. See, the entire mathematics is governed by business, So you need to learn this thing. It's all daily business, And people wanted to count, okay, certain how many assets, how much assets I have. Say, for example, how many cows I have in those days, right? So they started counting, right? So this counting led to the development of natural numbers. Okay, so this is something very common. So I'll give you this nice story. Oh, I have to be careful here, but anyway. Why this? Anyway. So set of natural numbers 1, 2, 3, 4, 5, 6, and so on up to infinity, right? But then there was a problem in the society. Okay. So problem is, so I am telling you because now you understand some mathematics, the kind of problem they faced solving certain kind of equations, which was difficult. For example, when we know about set of natural numbers, equations like x plus 2 is equal to 0. How will we solve? X plus 2 is equal to 0. There is a problem in this set of natural numbers because we have not invented negative numbers yet, right? So it's a very common problem in those days. So what they do? So they extended the definition of numbers to include negative numbers. Okay. 0 came bit late. Who invented 0, by the way? No. So Aryabhat never invented 0. This is wrong.
It was discovered.
Huh? You will not be able to find the correct answer. I know, even if you search on Google, that I know, I guess. So this is done by, because it's written in Indian literature, and you don't read those things, right? You look at Western education. But anyway, it's Acharya Gutsmat. So now, you need to search who is that guy, where to find information. That is, I leave it as an exercise for you, right? Acharya Gutsmat invented 0. And later on, actually, people have used it, but invention was pretty important. Of course, there is a lot of debate also, controversies. People will say that no, we invented or who invented. By the way, there is a Bhaksali manuscript found in Peshawar, Pakistan, which has the oldest written record of zero, basically. So zero was invented a bit late, but anyway. So this, you know, this thing from n. From set of natural numbers, they extended the definition to set of integers. I'm including zero for the convenience, but though zero was invented a bit later, set of integers are 0, plus minus 1, plus minus 2, and so on. You know about these things, right? Then what? Business continues for a couple of years or whatever. And then there was a problem, right? What kind of problem? No. Numbers so बाद में आएंगे ना. Equations. Which equation? Equations of the type 2x is equal to 1. Problem. Business stops for a while. Then people started looking how to solve this. And they further extended this to what is known as Q. I'm not sure why. Probably I am not very familiar with this pen, but anyway. Q is a set of rational numbers of the form P by Q such that P and Q. It's pretty strange. Anyway. Integers. And Q is not equal to 0. Okay. So this was set of rational numbers. I'm still calling it set, but then there were a couple of issues with this. There were equations like, which equation next? X square is equal to 2. I mean, just an example. So this equation has a problem. So you need to extend it further. And then you invented what? Real numbers. Real numbers are very beautiful, right? Why real numbers are very beautiful? You might have studied in calculus, right? Real numbers, नहीं पढ़ा नहीं होगा, थोड़ा बहुत पढ़ा होगा. It depends on which book you have used to study calculus. If you have not studied G.H. Hardy, calculus. So basically, G.H. Hardy course of pure mathematics is a very beautiful book, and you look at how Denikin cuts and real. If you really love mathematics, you can see how beautiful the things are. The structure of real line you can study and so on. But anyway, so that is about real numbers, and they were there were equations like x square plus 1 is equal to 0, right? So this was a problem. Then they further extended to what is known as a plus ib. There is some problem I need to. Such that a and b are reals, and I is a root of the equation I square plus 1 is equal to 0. Right? Fine. After that, what happened? Are there equations which we cannot solve? After this, if you create an equation with coefficients real or complex, you will be able to solve it. Of course, there is little issue here that degree n polynomial will have n root, that we know. But explicitly finding a formula, like we know how to solve a degree 2 equation, Sridharacharya formula you might have read, right? Then degree 3, Cardan's cubic solution. Degree 4, there is a formula. Degree 5, is there any formula? No. No formula for degree 5 or degree 6 and so on. So that's a interesting thing. And that was this. There is a lot of interesting mathematics using that. People have shown that in fact, Niels Henrik Abel has done a lot of work in this, and the invention of group theory actually, looking at the roots of the equations. Group theory you will probably hear some of your classes later on. I think we may talk briefly about group theory, but not too much. By the way, after this, there were other numbers like Cauchy numbers are there. They are discovered for hypercomplex numbers with 1 I, j, k, with I square is equal to -1, j square is equal to -1, k square is equal to -1, right? That kind of thing. The number is linear combination of these things. Okay. So 1 I, j, k. So like in complex it is 1 and I, right? Combination of 1 and I, right? A plus IB, 1 and I. And the scalar. So A plus B, I plus C, J plus D, K. Where I square is equal to -1, J square is equal to -1, K square is equal to -1. What is the use of these Cauchy numbers? May not be knowing in your wireless phone. Beautiful application. So everything, has a application. Every statement of mathematics has got an application. Do you know that? Everything. There are a lot of interesting mathematics which was discovered just by curiosity, and later on they found that there are nice applications, right? If you really want to see beautiful applications. Anyway, so we have these how many? N, Z, Q, R, and C. Which one is a field where we can play with all the 4 operations of addition, subtraction, multiplication, division? N is a field? No. Very good. Next is Z. Is it a field? No. Next is Q. Q का तो नाम ही है field of rational numbers, right? So field because you can do addition, subtraction, multiplication, division in the set of rational numbers, right? So it is a field you can play with every numbers. Then the next one is R, field of real numbers. You can play with, you can do all the 4 operations: addition, subtraction, multiplication, division. And the next one is C, field of complex numbers. ये सब तो बहुत ही मामूली बातें थी जो मैंने बताई ना, इट्स एलिमेंट्री थिंग. नाउ आई एम गोइंग टू आस्क यू सम नॉन ट्रिवियल थिंग्स. अब हम तुम्हारे दिमाग को कुछ घुमाएंगे, जादूगरी चीज दिखाएंगे, ठीक है ना? नाउ यू सी दैट वी हैव 3 थिंग्स, Q, R, C. Number of elements, how many elements are there in each? Infinite. What about finite field? Can I construct a field with only finite number of elements? That is a beautiful question. That has led to the development of these computers that you see here. Finite field. Unfortunately, ये ज़्यादा पढ़ाया नहीं जाता है कभी. पूरा अभी तक करके आया होगा ना 12th. Nobody taught. But this is something which one should give some flavor. I'm going to touch briefly. Very brief, So finite field. So you can see that Q, cardinality of Q is infinity, cardinality of R is infinity, and cardinality of C is infinity. Okay. So I am worrying about finite field. Less than infinity. So I actually use a lot of shorthands. I like it, Less than infinity means finite. So the first example that I'm going to take, I take all the positive numbers, say for example, and I divide it by 2. What are the possible reminders? 0 and 1. Either remainder is 0 or remainder is 1. So using this thing, we can construct a field. It is known as integer modulo 2, consisting of only two elements, 0 and 1, with operations plus 2 and multiplication of 2. Now, you should not believe me like this. So I'm going to make a table. Plus 2, 0, 1, 0, 1, minus 2, 0, 1, 0, 1. 0 plus 0 is 0 plus 1 is 1 plus 0 is 1 plus 1 is. So this is a interesting thing, right? 0 into 0, 0, 0, 1 into 1 is 1. Now, so we complete this table. This table is very useful to identify whether this set is a field or not. For example, I mean, closure is there and all those things are, you can see that everything is there. I am worrying about the inverses. So here you can see that 0 plus 0 is 0. That means 0 is self-invertive, right? And 1 plus 1 is 0. 1 is self-invertive because 0 is the additive identity, right? Additive identity. So that means both 0 and 1 has inverses. They are self-invertive. So essentially, every element should have an inverse with respect to addition, also with respect to multiplication. Then only this will become a field. So now with respect to multiplication, if we check, of course, we don't worry about 0. So 0 you can include. So we never look for inverse of 0 because we assume that whenever we are dividing, we will not divide with 0, right? So 1 into 1 is 1. That means 1 is self-invertive because 1 is your multiplicative identity. So basically, I just try to encircle multiplicative identity and additive identity. Okay, so this set is a field. What is the set? It is known as integers modulo 2. Modulo 2 operation means I have divided by 2 and look at, okay, divided by 2 and look at possible reminders. The reminders are 0 or 1. This is the smallest known field in this universe. The smallest known field, right? Where you can do all four operations: addition, subtraction, और क्या है? Multiplication and division. ठीक है? तो दो नंबर की फील्ड हो गई. इससे कम हो सकती है क्या? Because every field will require, because if you want to do all the four operations, you require at least additive identity and multiplicative identity तो होना ही चाहिए, right? At least those two things. दो से कम तो हो ही नहीं सकती, right? At least 0 and 1 should be there. Very good. So we have constructed field with two number of elements. Now we go a bit further. Can we construct field with three number of elements? Three number of elements. So I look at integer modulo 3. Elements are 0, 1, 2. I can make a table. 0, 1, 2. Multiplication modulo 3. 0, 1, 2. 0, 1, 2. 0 plus 0. 0 plus 1. 0 plus 2. 1 plus 0, 1. 1 plus 1, 2. 1 plus 2. 1 plus 2, 3. Modulo 3, which is 0. 2 plus 0. 2. 2 plus 1. And 2 plus 2. Very good. What about this? 0, 0, 0. Then we have 0, 0. 1 into 1, 1. 1 into 2, 2. 2 into 1, 2. 2 into 2. So now you can check there with respect to addition. This is the identity. I'm just encircling additive identity. This one is there, this one is there, this one is there, and multiplicative identity, this one is there, and this one. So now if you see 0 plus 0 is 0, so 0 is self-invertive, right? Self-invertive. 1 plus 2 is equal to 0. That means 1 and 2 are inverses of each other with respect to addition, right? And similarly 2 plus 1 is equal to 0. So 1 and 2 are inverses of each other with respect to addition. So with respect to addition, I can play with all the 4 operations anyway. What about multiplication? 0 we avoid. Then I should check for each other element, inverse should exist, right? So now 1 into 1 is 1. So 1 is self-invertive, fine. Because 1 is a multiplicative identity. And 2 into 2 is 1. So 2 is self-invertive. So we are done. Every non-zero element has a multiplicative inverse, right? And every element has a additive inverse as well. So this is a field. Field where we can play with all the 4 operations: addition, subtraction, multiplication, division. So this is a field, right? Any question? अगर ये सब समझ में आ गया तो ये तो मैंने दिया एग्जांपल 3, field with 3 number of elements. What about field with 4 number of elements? Who is going to construct? अब कुछ तो करो अपने आप. Field with 4 number of elements. Yes. Previous example, huh? We are dividing by 2 and looking at the remainder. 2 divided by 2, so remainder is 0. That's the operation. Okay. So now we come with G4. 0, 1, 2, 3. 4 elements. Integer modulo 4. Then I start to multiplication mod 3. Zero plus 0 is 0. 0 plus 1 is 1. 0 plus 2 is 2. 0 plus 3 is 3. 1 plus 0 is 1. 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 2, 3, 0, 1, 3, 0, 1. 0, 0, 0, 0, 0, 0, 0, 1, 2, 3. 2, 2 into 2. Now tell me, is it a field? Why? So first, let us check with respect to addition. So 0 is self-invertive. 0 plus 0 is equal to 0. Fine. What about 1? 1 and 3 are inverses of each other with respect to addition. 1 and 3 are inverses of each other with respect to addition. Fine. And 2 is self-invertive with respect to addition because 2 plus 2 is equal to 0. Right? What about multiplication? We circle multiplicative identity. So let us circle multiplicative identity. This is there and this is there. So 1 is inverse of itself and 3 is inverse of itself. So 1 or 3 का inverse so है. What about 2? So it is not a field. अब तो मुसीबत आ गई बड़ी भाई. So we need to do something. But before that, before moving further, I just want to take you to Z3, integer modulo 3. By the way, this Z3 is, Z word is used in America, right? So if you are from Western part, American, you can use Z. Otherwise, in Indian part, you can use Z, right? Z3 or whatever. So now, in this field, what is the value of 1 by 2? 1 by 2 is 0.5, right? यहाँ पे क्या होगा? तो 0.5 क्यों नहीं होगा? So 1 by 2 is equal to which number I should multiply 2 so that I will get 1? 2. So 1 by 2 is equal to 2. है ना विचित्र चीज? You see, 1 by 2 is equal to 2. It is not 0.5 as you might be thinking till now, right? Beautiful, right? 1 by 2 is equal to 2. So these kind of bizarre things you will see. Magic, okay? Magic you see. Now, so we have done with Z4, but Z4 is not a field with 4 number of elements, so there is a problem. Now, can you answer what about Z5? Is it a field? Integer modulo 5? You can verify by making these two tables, addition and multiplication. Z5 is a field. Z6 is a field? No, because 2 into 3 is equal to 0. Field has one very specific property which you use every day, but you don't know, which is the fact that A into B is equal to 0 means either A is 0 or B is 0. This is the property of field. If a set is a field, that means product of two numbers equal to 0 means one of them has to be 0, right? That you use quite often. But here, for example, in Z4, 2 into 2 is equal to 0. None of them is 0, right? 2 into 2 is equal to 0. Because 2 is a 0 divisor. 2 is known as 0 divisor. Similarly, in Z6, 2 and 3 are 0 divisor because 2 into 3 is equal to 0. Neither 2 is 0 nor 3 is 0, but their product is 0. तो हम मैथमेटिक्स को एक स्टेप आगे ले जा रहे हैं, राइट? सो नाउ योर ब्रेन थोड़ा सा एनलाइटमेंट हो रहा होगा, राइट? नाउ वी take it a little bit further and see, okay, so how do we construct? So anyway, so Z2 is a field. ये list बनाते जाओ. Z2 is a field. Z3 is a field. So I can say that Zn is a field. Can you tell me when? N is prime. Very good. So Zn is a field if and only if n is a prime number. Z2 is a field. Z3 is a field. Z4 is not a field. Z5 is a field. Z6 is not a field. Z7 is a field. Z8 is not a field. Z9 is a field. No, Z9 is not a field. Z9 is not a field. Then Z10, no. So you know, right? Z11 is a field and so on. So when you say that, who said that Zn is a field if and only if n is a prime number? You said, right? So now, can you prove it? बिना प्रूव करे कैसे होगा? तो आज चाय का कप लेके बैठना. So this is an exercise for you. T time problem. Zn is a field if and only if n is a prime number. Zn, integer modulo n, is a field if and only if n is a prime number. Okay? Integer modulo n, लिख दूं क्या? T time, right? Zn is a field if and only if n is prime. कितना टाइम बाकी है हमारे पास अभी? नहीं हो नहीं गया अभी तो बहुत टाइम बाकी है. So basically think एक थोड़ा सा मजा दे देता हूँ उसके बाद, ठीक है ना. So let us enjoy. So now I will try to construct field with 4 number of elements. And in order to do that, I will like to first ask you this question. Real से हमने complex कैसे बनाया? Set of field of complex numbers we constructed from field of real numbers, right? If you recall that, so we had real numbers. From real numbers, we constructed field of complex numbers by a plus ib such that a and b are in reals, and I is the root of the equation x square plus 1 is equal to 0. So this equation has no root over reals. X square plus 1 is equal to 0 has no root over reals. Its solution x equal to square root of minus 1 is in the complex, not in the reals, right? This is the technique you just master. So once you master this technique, I can use similar thinking to construct field with 4 number of elements from field with 2 number of elements, Z2. So we have Z2 here. So the question that I'm going to ask, here the equation was x square plus 1 is equal to 0. So on Z2, I have to find a equation which has no root. So if I write down ax square plus bx plus c is equal to 0, such that a is not equal to 0 and a, such a beautiful equation, right? Ax square plus bx plus c is equal to 0, where a is not equal to 0. I mean, and abc in Z2. Can you apply Shizaracharya formula now? आप क्या करें? This is something interesting thing. Another tea time thing, right? But let us show you few things. I'll do it few things here. Let us see. So since a is not equal to c, I know that both. I mean, all a, b, c, all scalars are in either 0 or 1, right? If a is not equal to 0, then a has to be 1. So the equation will become this. Where b and c are in Z2. That means now you are going to see the beauty of discrete math, right? What is the beauty of discrete math? B has 2 choice, C has 2 choice. So you can see how many equations are there. There are only 4. I can write all the 4 equations. X square plus x plus 1 is equal to 0. X square plus 1 is equal to 0. X square plus x plus 1 is equal to 0. X square is equal to 0. And x square plus x is equal to 0. Now tell me which equation out of these 4 has no root over Z2. Z2 has only 2 elements, 0 and 1. Discrete has, right? This is discrete. Only 2 elements, 0 or 1. So I can plug in the values. If I look at this equation, this has a root, x equal to 0. This is not going to work. This is not going to work. This has also x equal to 0. This is also not going to work. What about the first equation? X equal to 1 is a root because 1 square is equal to 1. So 1 plus 1 is equal to 0. Right? This is also not possible. Now, if you look at this equation, if I put x equal to 0, 0 plus 0 plus 1, which is not equal to 0. So 0 is not a root. If I plug in x equal to 1, 1 plus 1 is 1, which is not equal to 0. So this equation is exactly similar equation as x square plus 1 is equal to 0. Right? Here, this equation is not going to work because over z2 x squared plus 1 we can solve. Okay, x squared plus 1 we can solve. X equal to 1 is a solution. Right? So that means this equation is wonderful equation. So now you see, take this equation here. X squared plus x plus 1 equal to 0. Analogous to x squared plus 1 is equal to 0. And let me try to construct the field in the similar manner. So I am going to take what I am going to do, x squared plus x squared x squared plus x plus 1 is equal to 0. Okay, and I am going to construct field. I will denote it by GF4. GF stands for, it's the name, Galois field, Galois, Galois field. Okay, Évariste Galois, who invented these things. Évariste Galois, Galois field with 4 number of elements. I can denote it as A plus omega B such that ओमेगा नहीं लेते हैं, ठीक है, A plus अल्फा भी ले लेते हैं, ठीक है, या ओमेगा ले लें, क्या बोलो, such that A and B are in Z2. Field with 4, see, just like A plus IB, A plus omega B. But what is omega? Omega is the root of the equation x squared plus x plus 1 is equal to 0. आगे analogy पूरा, right? We look at a base equation, right, and see if it has no root in the base field, right? And suppose omega is a root which is outside the field. Just like here, we have done the same thing. Okay, just like here, I is the root of this equation. I attach A plus IB and like this, right? Same thing I have done, A plus omega B, where A and B are in Z2, and omega is the root of this equation. Now what? Let me now simplify the expression. So we have field with 4 number of elements. A plus omega B such that A and B are in Z2. So what are the possibilities? When A is 0 and B is 0, 0, 1, 1 plus omega and omega. ये 4 एलिमेंट आएंगे. Now you will ask me many questions, so I am ready with few things here. Now let me show you. Now I am going to do what? 1 plus omega is omega squared. Do you agree? Because 1 plus omega square is equal to 0. This implies that omega square is equal to minus 1 plus omega. Which is same thing as 1 plus omega. You may ask how. पूछोगे क्वेश्चन यहाँ पे, right? Minus 1 is same thing as plus 1, don't you think so? See what is happening? Every element in ZF4 is A plus omega B, where A and B are in Z2. So the coefficients are in the ground field. Okay? So whenever we are doing so, 1 plus 1 in the ground field, 1 plus 1 is equal to 0. So 1 is equal to minus 1, right? So it's a ground thing, right? So you observe the beauty, right? Now you, one more beauty. What is the value of omega cube? omega cube is equal to omega into omega. Omega square is equal to 1 plus omega. We just saw that this is into omega is equal to omega plus omega square plus, but omega plus omega square is equal to 1 because 1 plus omega square is equal to 0. See. Now I am going to ask you the mysterious question. Mystery is, looks like this is complex cube root of unity, right? Is it the case? This is different world actually. Okay, this is not that omega because their omega, you know, is in terms of complex numbers. There is no complex number here. There is no complex number here, right? This is a different world altogether. Got it? So now you can do these calculations, right? Easily. Only that I can. Yes, any question? So now, so there are three representations of this field which I want to mention. GF4 is equal to 0, 1, 1 plus omega and omega. This is known as polynomial representation. I will tell you why. Because this is a polynomial in omega, right? Then we have 0, 1, omega square and omega. Power of omega, right? Power of omega representation. Then we have 0, 0. 1 is what? 1, 1 comma 0. If it is a plus omega b, right? Both are 0, means 0, 0. A is 1, b is 0. You will get 1, 0. And 1, 1, and then 0, 1. So you are getting bits representation. Now you see, you might have heard of byte. Byte suna hai na? B-Y-T-E, byte. Byte means 8 bits. Those 8 bits lies in which domain? That is fine. Bits means 8 bits. 8 bits, 8 bits. So here there are 2 bits. 2 bits means 4 elements. Field with 4 number of elements. So 8 bits means field with how? 2 raised to power how many? 8. 2 raised to power 8, right? 2 raised to power 8 is what? How much? 256. That's why we know that every media file, whether you take PDF, doc, is converted into byte strings. Byte belongs to field with 256 number of elements. Entire backbone of computers, you know, based on discrete math. Very simple. You got the idea? Bytes. Bytes are elements of field with 256 number of elements. Okay? Yes. Byte means 8 bits, right? So how many total number of elements possible? In 2-bit case, you got 4 possibilities, right? 0, 0, 0, 1, 1, 0, 1, 1, right? 4 strings were there. Each can be represented by power of omega or a polynomial form of omega, right? 0, 1, 1 plus omega and omega. Similarly, when you go to field with 256 number of elements, 2 raised to power 8 possibilities will be there, right? For 8 bits, right? If I ask you 8 bits, how many possibilities are there? 2 raised to power 8? 2 choices for each. So 2 raised to power 8 is 256 number of elements. So maybe you can construct field with 256 number of elements. थोड़ा सा हाथ में ज़्यादा टाइम लगेगा, but I think पहले शायद इसके लिए प्रोग्राम लिख सकते हो, but I think for this one, I think you can try next smaller cases by hand. So आज की चाय का तो इंतजाम नहीं हुआ हो तो कल you can do. So what you can do, construct a field with, so we have done with 4. 4 I have shown to you, right? 2 is there, 3 is there, 4 is there, 5 is there, What about 6? 6 is not possible. If you think a little bit, you realize it. 6 is not possible. Okay. And 7 is there. Think about it. Why 6 is not possible? Because all these questions I ask in the exams, I shake your brain. I want to ask, understand what you think. 6 is not possible. 7 is possible. Construct field with 8 number of elements. It is possible. Field with 8 number of elements. Only 8. 8 के लिए I can give you some hint. So I will look at, in order to go from Z2 or ZF2, Galois field with 2 number of elements, or Z2, integer modulo 2 with 2 number of elements, 0, 1, to Galois field with 4 number of elements, what we have done, we have actually used a degree 2 polynomial, right? X square plus X plus 1 is equal to 0. Now I am going to look at degree 3 polynomial. So AX cube plus BX square plus CX plus D is equal to 0, where A, B, C, D are in Z2 and A is not equal to 0. So now tell me how many polynomials are possible? 8. Which one will work for the construction of the field? X cube plus X square plus 1 is equal to 0 is one polynomial. Very good. We have found another one. X cube plus X plus 1 is equal to 0. अब क्या करें? दो रास्ते. सिक्का उछालो, right? Now you see the real beauty of mathematics. You pick up anything. Somebody will pick up X cube plus X plus 1 is equal to 0. Somebody will pick up X cube plus X square plus 1 is equal to 0. You will get field with 8 number of elements. And the resultant field are isomorphic, means they are, algebraically, the structure is same. That is the beauty. See, isomorphic word suna nahi hoga shayad, nahi? Means the algebraic structure is same. Algebraic structure is same. So it's kind of renaming the elements. Okay, renaming the elements. That's all. Essentially. So no matter which polynomial you pick up, either you pick up X cube plus X plus 1 is equal to 0, or you pick up X cube plus X square plus 1 is equal to 0, you will get field with 8 number of elements. Okay. So that is a beautiful thing. Now this is a tea time. So you can take one big cup of coffee and construct field with 8 number of elements. You should also construct field with 9 number of elements. 9 number of elements के लिए क्या करेंगे? Z3 लेंगे हम. Base में we'll take Z3 and take 3 square is 9, right? 3 square is 9, right? So if 3 square is 9, so we can take degree 2 polynomial over Z3. Degree 2 polynomial over Z3 to construct field with 9 number of elements. Okay, so you need to take ax square plus bx plus c is equal to 0, where a is not equal to 0 and a, b, c belongs to Z3, not Z2. So the equations will be more, you find out which one will work and so on and so forth, right? All those calculations you have to do. Okay, so yes. So I am constructing from GF3, Z3 to ZF9, 3 square. So basically I should do like this. See, the tower goes like this. Z2 or GF2, this goes to GF2 square, which is 4. This goes to GF2 cube, 8, and so on. This is when base 2 is taking, you're taking base 2, Z2, okay, all binary. And in general, you can take ZP. P is a prime number. Then you construct Galois field with P square number of elements. Then you construct Galois field with P cube number of elements, and so on. Galois field with P raised to M number of elements, where P is a prime number. So in your case, P is equal to 3. We will use this case. Got it? This is how the, so this is ZP. So in general, if you want to construct field with, no, this construction, I mean, this intuitive thing shows you that field with 6 number of elements it is not possible, because a field with Q number of elements exists if and only if Q is a prime power. Because Q is a prime power, right? Power of prime. With 6 number of elements, you will not be able to construct a field. Right? 7 is possible, 8 is possible, 9 is possible, 10 not possible because 2 into 5 is equal to 0. 11 is possible, 12 not possible, 13 possible, 14 not possible, 15, 16. Very good. So you understood the basics of finite field. Okay. You have enough cup of coffee and then you start working on it. Some examples: field with 9 number of elements, field with 8 number of elements. So I think in the class, some of you can take degree, some of you for the construction of field with 8 number of elements, some of you can take x cube plus x plus 1 is equal to 0, and some of you can take x cube plus x square plus 1 is equal to 0, and then compare. Discuss on the WhatsApp group what you are getting. You look at the tables. And then if somebody can tell me the relationship between the two, that is the beauty. And I want somebody to find that beauty, right? What is the relationship? So if I take one polynomial and construct field with 8 number of elements, I take another polynomial and construct field with 8 number of elements, what is the connection between the two? Right? Any question? Yes. 16. 16 2 raised to the power 4. So I need to take a degree 4 polynomial over field with 2 number of elements. Degree 4 polynomial, which has no root in the ground field. See, the condition is that the polynomial should not have any root in the ground field. Okay. So we have talked about modular arithmetic and fields. This was our second lecture. I hope you enjoyed it. After that, yes. What you do in football field, you play football. The cricket field, you play cricket. Similarly, in this field, all the computer business, all the packets, data packets are elements of finite field only. As I told you, byte string that you convert, if you write a program for any PDF file or doc file or PowerPoint, convert it into computer string, it will be byte string. Each byte, that means 8 bits, belongs to field with 256 number of elements. ASCII codes are like that. Remember, 256 number of elements. Direct connection. But ये सब interesting चीजें पढ़ाई नहीं जाती हैं. That is another thing. But normally people don't touch, right? But I don't know why. But anyway, that's a thing. Thanks a lot. Next class we will do